A long time ago in a galaxy very, very close. You are an explorer from a different time, and you encounter a hot, lush, green and blue planet with a single giant ocean and a single giant continent. Sounds very much like science fiction, doesn't it? However, if you had visited Earth hundreds of millions of years ago, this is roughly the scene that you would have seen. If we break up this giant continent and shift some of the pieces around, we can soon come up with an arrangement that is much more familiar to us. Take a look at the coastlines of Africa and South America. Now, just by looking at them, you will likely notice a similarity in the coastlines of the two. This similarity was first noticed by a Dutch mapmaker named Abraham Ortelius in 1596. Of course, it was only shortly before this that European exploration had mapped enough of the continental coastlines to be able to draw them with any accuracy, so that someone could see the coastlines to put them together. Regardless, it wasn't until 1912 that someone came up with a full, thought-out theory of why they might look like this. Alfred Wegener was a man of many talents: meteorologist, geophysicist, and polar explorer. While looking through a book of fossil occurrences, he read how many identical species were found on opposite sides of the Atlantic Ocean, in both eastern South America as well as Western Africa. As well, many of these animals were land dwellers, unable to cross major oceans.
Alfred Wegener was not actually the first to notice that fossils in Brazil and Africa shared a surprising number of similarities. What was the prevailing theory at the time to explain these occurrences? Was it land bridges that were submerged just below sea level? Or an expanding Earth creating oceans between lands? Or did animals cross over ancient ice bridges? The main theory to explain the distribution of fossils at the time was that there were giant submerged land bridges spanning thousands of kilometers just below sea level. So A is the correct answer. Wegener, thinking of the fit of the continents, took a slightly different approach. Instead of animals moving across land bridges, what if it were the continents themselves that moved?
Although Wegener had both fossil evidence, in the form of the same animals found on distant lands, as well as the observation that continental coastlines seem to fit together into a single whole, he nonetheless lacked any proper mechanism for why the continents should move. As such, it was some time until his ideas were accepted by the general scientific community, let alone the public at large. It wasn't until deep-sea exploration during the 1950s and 1960s that scientists began to build up a larger body of evidence, and the first theories of plate tectonics emerged. In particular, the observation of mid-oceanic ridges led to a number of new discoveries and ideas, such as how new oceanic crust can be produced at the volcanically active rifts where two plates move away from one another, and the incredibly deep trenches where one plate is subducted beneath another. With a building body of evidence, eventually geologists came around to the idea that, indeed, the Earth does move. With advanced GPS satellite tracking techniques, we can today follow the movement of the different plates and observe how fast they are moving relative to one another. These speeds are usually relatively slow, with movement on the order of millimeters per year. However, major events can sometimes lead to truly big shifts. For example, during the Japanese earthquake of 2010, the recording station in Japan recorded a jump of almost 3 meters in just a few minutes.
Think of some famous structures built in North America about a century ago. The Statue of Liberty is a little over 100 years old, while the Empire State Building is just under 100 years old. Now, both of these structures have been standing in New York for a long time. They haven't moved, or have they? Because the North American continent has been moving relative to the center of the Earth, these structures have actually been moving as well. Relative to the center of the Earth, take a guess as to how far these structures have moved over the last century. Is it a few millimeters, a few centimeters, a few meters, or a few kilometers? The answer is about 3 meters, or roughly 10 feet, so C is the correct answer. Although continental plates move very slowly every year, about as fast as your fingernails grow, over millions of years, the distances covered become quite substantial.
What we can see on the Earth is but a very thin layer. The Earth can be compared to an avocado, composed of several different layers. In our everyday lives, we only usually see the most superficial part of it. However, what if I told you that right now you were standing directly above roiling hot molten rock? Well, it's true. In fact, no matter where you stand on Earth, you are standing above molten rock. That's because, although the outermost layer of the Earth is made of hard rock, the consistency and composition changes as you move deeper and deeper. This outermost layer, called the crust, is between 5 kilometers to 25 kilometers thick, depending on the spot you measure it at. Although 25 kilometers is a considerable distance, the crust is really just that, an extremely thin layer that surrounds the Earth. Directly below the surface of the Earth, or the crust, lies another layer called the mantle. The mantle is a somewhat mobile layer that is able to flow, albeit very slowly. Going deeper still, we have the outer and inner cores. Both of these are made up primarily of iron and nickel, while the outer core is a liquid and the inner core is a solid ball. The temperature of the inner core is somewhere around 5,700 degrees Celsius, around the temperature of the sun. When it comes to the movement of the continents, most of what we need to know happens in the outermost layers of the Earth. We have already said how the outermost solid layer is called the crust, and how the continents and ocean basins we see on the surface are all part of this crust. The crust, along with the uppermost part of the mantle, is often called the lithosphere. Below this lithosphere is what is called the asthenosphere. The asthenosphere is only part of the mantle, but it is relatively fluid and can flow, although it flows more like Play-Doh than water.
Which layers of the Earth are solid? Check all the answers that you believe are correct. Is it the crust, the mantle, the outer core, or the inner core? The crust and inner core are both solid, while the mantle and outer core are fluid. So the correct answers are A and D.